Okay, I think we can start already. It's already 4:02. Before I start with today's lecture, are there any questions about yesterday's lecture or about something else that you would like to ask now? Okay, it seems there are none, but you can feel free to ask me during the lecture or after the lecture. You can send me an email if you will, and I'll be happy to get back to you. All right, let's IR symmetries and GR. Lecture 2. Okay, so let's do a very quick recap on what we discussed mostly in the last lecture. I sent the forms for the attendance. It is in the chat right now, and as yesterday someone asked for it because they came in late. Feel free to send it again, and I'll try to send it a few more times during the lecture. Okay, so as a recap for last lecture, what we discussed is we want to get our goal in this course is to understand BMS symmetries, which are symmetries at infinity in general relativity, specifically at infinity in asymptotically flat spacetimes. So spacetimes whose gravitational field gets very, very weak when you go very, very far from the matter sources. So a few examples would be stars, black holes, galaxies, planets, stuff like that. So essentially anything that doesn't involve cosmology. Yes, I think that's a good model. Okay, so that is what we want to understand. We want to understand BMS symmetries, and a few motivations for this. The applications I mentioned. This has to do with soft theorems in quantum gravity. It has to do with the memory effect, which we hope to detect in future gravitational wave experiments. It can be used to construct interesting vacua in quantum field theory in space-time, and so on and so forth. So we want to understand these symmetries. In order to understand the symmetries, the first step that we took was to understand what is the mathematical way of describing symmetries. So this is the first thing we try to understand mathematically, which is how do we describe symmetries in a mathematical language, in a mathematical parlance. And the way we decided to do this, we were inspired by the particular case of rotations, and this led us to the notion of a group, which is an algebraic construction. In the sense that it is an algebraic construction, it is very similar to a vector space, but it is simpler. It has less axioms, and it has only one operation. And a group is the basic structure that we need to describe what is a symmetry. To recap what a group is, the basic idea is that we are going to have a pair composed of a set G and a function dot that goes from G, Cartesian G, to G. So it eats two elements of the group and it spits out another element of the group. This function sometimes is also called product, the group operation, and stuff like that. So the terminology varies a little bit, but it's usually quite intuitive. So we're going to use whichever name it is convenient to discuss in the group. We usually call it product. So you have the set, you have this product, and you need a few conditions for us to call this pair a group. So the first of them is that dot should be associative. And by this, what we mean is that you do not have to use parentheses when writing products of many elements of the group. Specifically, if we write G1, G2, G3 with parentheses in this way, this is the same thing as changing the order of the parentheses. And this is something, this condition I argued is because when we're dealing with symmetries, we can just do each transformation step by step. So when we're dealing with symmetries, we can understand as first doing, for example, G3 and then G2 and then G1, and you just go in this order. And this is my physical argument for why we should require associativity. But the mathematical argument is we should require associativity because that is very useful. So it leads us to a very rich theory. It leads us to a very good mathematical model. So we can do a lot of stuff when we ask for associativeness. The second condition that we asked is the existence of an identity. And by this, it means that there is some guy, E, in the group. We usually use this letter E. When we're talking about abstract groups, when we're talking about matrix groups, this will typically be the identity. So you pick, there is this element E in the group, such that for any element in the group, it holds that E times this element equals this element times E, which is equal to this element. So there is this group element, which is the identity, which essentially is the transformation that does nothing. So in terms of symmetries, this is the symmetry that we get by not doing anything to the physical system. If we don't change the physical system, of course, it looks the same before and after the transformation. So we always have an identity. And finally, the last axiom is the existence of inverses. And the basic idea for this from a physical point of view is that if you do a transformation and it is a symmetry, you can reverse that transformation. It should also be a symmetry. Because if a system looks the same before and after the transformation, then it also looks the same after and before the transformation. And mathematically, we say that by saying that for every G in big G, there is a G inverse in big G, such that G times G inverse equals G inverse times G, which equals the identity. So you can always invert a group element. And these are the basic axioms for a group. These are the basic ideas for what a group is. As a few examples, we saw the orthonormal groups, which are ON. These are matrix groups, so they're formed by a matrix, by matrices R. They are N by N real matrices. This is the symbol. Okay, so MN with this blackboard bold are the N by N real matrices. And they satisfy this condition that R transpose times R equals the identity. So this are the orthonormal groups. We also consider the special orthonormal groups, which are composed of the orthonormal matrices with positive determinant. So these are the groups that involve rotations in n dimensions. So this considers rotations in 3 dimensions, which was our starting construction, but it also goes up to rotations in an arbitrary number of dimensions. Also of interest for us was the Lorentz group, both the general Lorentz group and the restricted Lorentz groups. So the full Lorentz group is a pseudo-orthogonal group, which means that you now have one dimension, one direction that is different from the other ones. So the way we defined it was that it was composed by matrices lambda, which were 4x4 matrices, and they satisfied this condition here, where eta is a matrix representing the Minkowski matrix. So in my sign convention, it is minus 1, plus 1, plus 1, plus 1. So this is very similar to the group, to the orthogonal group, and the orthogonal group only has plus signs. So you can notice here, for example, that O40 equals O4. We then decided to investigate the subgroups, the smaller groups that fit inside this group. And there were 4 connected components. So O31 is a Lie group, which means it is a continuous group. You can understand it not only as a group, but also as a manifold, which is a space in which we can do calculus. And when you take this point of view, you can see that O31 is formed by 4 pieces. So we have this 4 pieces here, and you have the identity in this first piece here, and you have a few reflections that take you to this other islands, so to speak. So if you do a spatial reflection, you get here. If you do a time reflection, you get here. If you do both, you get to this 4th island. And then we have a few subgroups in here. We have first this subgroup here, which is what we call SO31. This is the subgroup in which the determinant is positive. It's +1. And we also have the orthogonous subgroup, which is this guy here, O+31. It has the property that lambda 0 is positive. When we take the intersection of these two groups, we get this subgroup here, which is the restricted Lorentz group, or the proper orthogonous Lorentz group. We have these 2 names. And this is the group you're most interested in, especially because weak interactions, for example, break these other symmetries. So in practice, in nature, when we are considering fundamental physics in a flat space-time, this is the symmetry group for the space-time once you consider that the other symmetries are broken by your interactions. So this is the most important one. And even if you don't want to consider what the other interactions break or don't break, you can focus mainly on this guy here and then just consider the other ones by adding spatial and time reflections. So this is what we did last time. Let me just outline our plan for today, assuming everything goes with a better goes a bit more fast than yesterday. I got too excited in the introductions yesterday. So our plan today is first to continue the discussion about groups and discuss specifically the Poincare group, which is a group that is larger than the Lorentz group, and it has the full group of symmetries of Minkowski spacetime. So this is going to be a 10-dimensional group, and it has 10 free parameters, in the sense that it is a Lie group, and to describe a given point in the group, a given point in the manifold, you need 10 coordinates. So we're going to get to the Poincare group, and later we'll go to the next module of the course, so to speak, which are symmetries in curved spacetime. And what we're going to do here, we need to study maps between manifolds, Lie derivatives, which are the basic notions we need to discuss continuous symmetries in a spacetime, and then we're going to go to Killing vector fields. While this expression may be weird if you never saw it before, I should mention that killing is a name. So this is a capital K, and so it has nothing to do with the act of killing. It has the name of a scientist. And then, if time allows, we're going to go to 2 case studies, which will be symmetries in the 2-sphere, the 2-dimensional sphere, and in Minkowski spacetime in 4 dimensions. I'm not fully sure if I will go through all of the details in these discussions. I may skip a few details to go a little bit faster. But in any case, you can check them in the lecture notes, which are already available at the school website. So if you want to see the details with a little bit more care than I do in the lecture, you can check the lecture notes, and they're written there, or they give references to other texts that do in finer detail. Okay, so this is the recap and the outline for today. Are there any questions? All right, it seems that there are not. So I'll get started with the Poincare group. All right, so what we're going to be interested now is to study the coordinate transformations in Minkowski spacetime that keep the expression for the Minkowski metric invariant. So what do I mean by that? We're going to consider transformations of coordinates. So we're going to take x mu to x mu prime, which is going to be some function of the old coordinates. So we are going to map the old coordinates to new coordinates. And I want to do this with some ground rules. So what I want to do is I can, in principle, consider any such coordinate transformation when I'm dealing with relativity. So for example, this could be a coordinate transformation that takes Cartesian coordinates to spherical coordinates. It could be a coordinate transformation that takes the standard Cartesian coordinates, tx, y, z, to retarded and advanced time coordinates. So I could do, for example, define u equals t minus x and v equals t plus x, while I keep y and z unchanged. And I could consider any of these sorts of coordinate transformations. But I will be particularly interested in coordinate transformations that obey the following rule. I want them to keep the coordinate expressions of the Minkowski metric unchanged, which in symbols means that I want to have this condition satisfied. So the Jacobian matrix, yeah, maybe it is Jacobian, but that's not the point right now. So there's Jacobian matrices for the coordinate transformations should satisfy this condition. You may recognize this condition as being precisely the condition that we used earlier to define what is a Lorentz transformation. So a Lorentz transformation would be an element of the Lorentz group would be precisely 1-1 tensor such that this condition is satisfied. So what I'm asking is that this derivative here corresponds to a matrix of this form here. It should be an element of the Lorentz group. So what I'm asking is essentially the following differential equation. I want for this equation to hold for my coordinate transformation. So the most general coordinate transformation that has this property here, this property here is going to be a coordinate transformation that satisfies this differential equation. I am not assuming here that the coordinate transformation must be linear. It could be, in principle, any coordinate transformation. I'm picking the most general coordinate transformation and then imposing this condition here. Under this condition, I immediately get this differential equation. I can then integrate this differential equation to get that x prime must be given in terms of x. of the original x by this expression here. It's going to be a linear term plus an integration constant. So this is the expression I get for the general coordinate transformation, the most general coordinate transformation that preserves the components of the Minkowski metric. So when I do this, I get the transformation with this appearance. Now I know that I can treat lambda as a matrix, so it makes sense to look at this equation in a matrix notation. So I'm just going to pick and denote, for example, x is going to be x0, x1, x2, x3. I'm just going to put the components in a matrix, and I'm going to write this as x prime equals lambda times x plus a vector a. So you see that what we have here is not really a linear transformation. It is what we call an affine transformation, because it is linear plus an inhomogeneous term. So a non-homogeneous term, inhomogeneous. So this is the general transformation we get if we want to preserve the coordinate expressions of the Minkowski metric. So we're going to have this. And hence, the general transformation that we get, the general transformation that we get is we do this here. We make this map here. And we see that the transformation is then parameterized by two objects. We have the general transformation can be completely described if we give the Lorentz matrix lambda, which I'm going to assume to come from SO plus 3,1, so from the restricted Lorentz group. Of course, if you wanted, you could also consider the more general case in which lambda comes from the full Lorentz group, which is just the pseudo-orthogonal group 3,1. But as I said before, I'm going to restrict my attention to SO3, SO plus 3,1, simply because it is simpler, and I don't need to focus about all the structure of O31, and I just focus on one connective component, which is easier. So I'm assuming lambda comes from here, and this condition is necessary because in my differential equation, I had that this lambda here satisfied this expression here, which is exactly the definition of a Lorentz transformation. And in addition, I have this inhomogeneous term. This is just an integrating constant. So this guy is any vector in R4. So this is the general shape of my transformation. This lets me define a new collection of transformations, which I'm going to call ISO plus 3,1, which is given by pairs formed by a matrix lambda and a vector A, such that lambda is a Lorentz transformation, and A is a four-dimensional vector. So this is the collection of transformations with this property that I wanted, that it preserves the components of the Minkowski metric. And the reason I'm using this specific notation here, there are other notations that you can find across physics. So for example, I'm using this notation, which is a bit more group theoretic, but there are people who also write the Lorentz group here as, for example, L. There are people who write this guy here as P. It depends on the author. I decided to go in this notation. I simply like it because it is quite specific about which particular group I'm talking about. So this tells me it is orthogonal, this tells me it is proper, this tells me it is orthogonal, and I tells me it is the inhomogeneous group. So by inhomogeneous, we can call this the inhomogeneous Lorentz group, or as it is more commonly called, it is the Poincaré group. But I still didn't show it is actually a group, and it is not even clear what exactly is the group product. To understand what is the group product, let us consider how two of these transformations compose. So first, I'm going to consider the transformation that takes me from x to x prime, which is given by lambda x plus A. Then I'm going to consider a second transformation, which takes me from x prime to x double prime, which is given now by lambda prime x double prime plus A prime. So I'm considering these two transformations in sequence, and my question is, what is the transformation from x to x double prime? And we can just do this by simply, there is only a single prime in x. We can do this by simply substituting this equation into the following equation. So what we get is that x goes to x double prime equals lambda prime times lambda x plus A prime. So we can now just compute this expression and find that x go to x double prime equals to lambda prime lambda x plus lambda prime A plus A prime. Okay, and we see that this is actually still a Poincare transformation. The reason for that is that this is a composition of Lorentz matrices, and since the Lorentz group is a group, we know that this guy belongs in the Lorentz group. This guy is still an element of R4, and this guy is an element of R4. Hence, this sum is an element of R4, which means that indeed what we get here is still an element of the Poincare group. So this transformation is indeed an element of the Poincare group, and you can check the validity of the order group axioms. So just to give a better notation for this, we have that lambda, and if I apply lambda prime A prime after I apply lambda A, what I'm gonna get is lambda prime lambda prime A plus A prime. So this is the notation I'm going to use to the products in the Poincare group. And the effect of the product, what the product actually does, is this expression here. And you can check that this is indeed associative and the other properties. I heard an open microphone. Are there any questions? All right. If there are any, feel free to interrupt me. Just as an example, let us find the identity for this transformation by looking at this rule. We can check that it is going to be given by the identity and the vector 0. So if you use the identity matrix and the vector 0 on any transformation, what you're going to have is the identity times lambda times the identity times alpha plus 0. And this here is exactly the original transformation. You could also check on the other side, and you're going to get the very same result. So this is the identity for the Poincare group. You can also check what is the inverse. The inverse is going to be given by, let me see, it's going to be lambda inverse. And about A is a little bit more complicated. I think it's going to be lambda minus 1 times A. Let's check. We get lambda minus 1. So this is the first bit. Then we have lambda times lambda minus 1 times A plus A. Okay, I missed the minus sign here. There's a minus sign here. And then we get now the identity minus the identity times A plus A, and this is exactly the identity 0, which is the identity of the Poincare group. So you see, you still need to check for associativity. I'm not going to do this here, but you can do it at home. And at the end, you do conclude that the Poincare group is indeed a group, as you would expect. What is interesting now for us to see is that there are two particularly important subgroups of the Poincare group. The first of them is going to be the following. We're going to consider the group which is formed by lambda 0, where lambda is a Lorentz matrix. And using that composition rule for the Poincare group, you can check that indeed, if you get two Lorentz matrices here, both consider the Poincare group elements with this look, they're going to have lambda prime lambda, and this is going to be 0 because both A's are 0. So this is indeed just a copy of the Lorentz group. So this guy here is isomorphic to the Lorentz group. And the other group, which is interesting for us to consider, is formed by the identity as the Lorentz matrix and by an arbitrary vector. So we're going to consider this guy here, where A is any guy in R4. This time, the composition rule tells us that 1A composed with 1A prime of 1A is going to be given precisely by 1 A prime plus A, which you can check by using the group law. We find it over here. So this group here is actually isomorphic to the group R4 with the operation of addition. So it is the vector space R4 with the operation of addition. So this is actually a group. As I mentioned in the last class, every vector space is a group under addition. So we have these two particularly interesting subgroups. And why exactly are they interesting? The first reason is this is exactly the Lorentz group. So these are the Lorentz transformations, which are the Poincare transformations without translations. And on the other hand, these here are exactly the translations. So they are exactly what I get when I change the origin of Minkowski spacetime. So these are the two stereotypical Poincare transformations. So I have either a Lorentz transformation or I have a translation. And the general Poincare transformation is going to be a mixture of these two. And we would like to understand how exactly these two transformations mix together to form a Poincare transformation. And in particular, are all Poincare transformations just a mere composition of a Lorentz transformation and then a translation? Can we always write a Poincare transformation by first making a Lorentz transformation, a pure Lorentz transformation, and then making a translation? Or do they need to be combined in a more complicated way than a mere composition? So this question is a basic question for understanding how exactly the Poincare group is structured. So to understand this, the first thing we're going to notice is a particular property of the translations within the Poincare group. So recall that if we have an element lambda b of the Poincare group, its inverse is going to be given by lambda minus 1 minus lambda minus 1 b. This is the expression we just derived for the inverse. So this is the inverse of a generic element of the Poincare group. Now let me consider a particularly funny expression with the Poincare group elements and with translations. I'm going to pick lambda b inverse times a pure translation times lambda b. So this is going to be given. First, I'm going to just open up this inverse. I'm going to use this equation over here. And what we get is this expression, which is just what we just wrote. And then we're going to make this composition here, the second term. We can do it in any order because groups are associative. But I'm going to choose to do in this particular order just because I want to do it like so. The way we end up getting is going to be given by lambda with a plus b. So you just use the group composition law and you're going to find this expression here. Now we want to do the next product, and what we are going to get is the following. We're going to get lambda minus 1 lambda. And then we have this slightly weirder expressions here, which are going to be a bit more complicated, but they are going to be given at the end of the day by this expression here. So we get this thing here. And when we simplify everything, what we get is that we only have an identity, and on the other entry you have lambda minus 1 times a. So this is the result. Why exactly is this interesting? This is interesting because we took a general group element G, and we made what we call a conjugation. So we multiplied by G and by G inverse on either side of the translation that we wanted. I'm going to call the translation N here. So we made this calculation, and this result was still a translation. So if you do an arbitrary Poincare transformation, and then you do a translation, and then you invert the original Poincare transformation, what you get is still a translation. It doesn't need to be the same translation. So you can notice here that we started with a translation A, and we ended with a translation lambda inverse A. So you actually change the final translation. You change the translation when you do this conjugation by Poincare transformations. However, it still is a translation. And this might seem silly, it might seem just an odd curiosity, but this sort of property is very important in group theory. This property is what defines a so-called normal subgroup. Normal subgroup. A normal subgroup is the following. We have a group G, and we have a subgroup N inside G. So we start with this, and we're going to say that N is normal, which we write as this funny notation with a triangle. N is normal as a normal subgroup of G. If and only if for all N in N, it holds that G inverse N, G is in N for all G in G. So when you conjugate a normal subgroup by any element of the group, you still end up with the normal subgroup. So I can pick any element inside the normal subgroup, make a conjugation, and I will not leave the normal subgroup. Again, this might sound silly and just a very abstract definition. So why is this interesting or important? And the reason is the normal subgroups are very fundamental in group theory. You see, a construction that you have in many branches of mathematics is what we call a quotient structure. So you can define, for example, you can take quotients of a space by a smaller space and get a different decomposition. You can decompose the space in many pieces. And what is interesting here is the following. When you have a normal subgroup, you can define what we call the quotient space G quotient N. So this is going to be a smaller group, a smaller subgroup inside of G that ignores what happens in the normal subgroup. So this is going to be a simpler version of G, and at the end of the day, you can write the full group G as a suitable product of this sort of group, of this quotient, times, let me write it with quotation marks here because I have not defined a product of groups, but it's going to be times N, and this is going to be the original group. So I can decompose the group in smaller pieces and study one of them at a time and get more information on the full group G by taking a look at what happens in each of those pieces. Now, we're not particularly focused or particularly interested in exactly quotient structures here. We're more interested, in fact, in this guy here. We will be interested in defining what is a product, because the Poincare group can be naturally written as what we call a semi-direct product of two groups. So that is precisely how the Poincare group is composed of Lorentz transformations and translations. So what we're gonna want to do here is the following. The next point, yeah. Another important thing about normal subgroups is the following. Consider now that you have a subgroup H inside G. Now consider this new space, which is G minus 1. Yeah, I'm picking G and G. And we just conjugate the whole group. So this is going to be given by the element G minus 1, H, G, where H lives in H. So we're going to consider this new space. For a general subgroup H, this guy here is not the same as H. So you actually have many copies of the subgroup H inside the group G. So you don't have a unique subgroup. You have actually many different copies of the same subgroup inside G. So you can't say which of them is the true H, so to speak. But if you have a normal subgroup, then it does hold that G minus 1 times N times G equals N by definition. This is exactly the definition of a normal subgroup. So when we have a normal subgroup, you sort of have a unique subgroup. It is the unique subgroup N that you have inside G. You don't have many copies of it. You have only one. So this is the our main interest in normal subgroups. So this is what we are really interested in. And what we showed down is that R4 is a normal subgroup of the Poincare group. So the translations are indeed a normal subgroup of the Poincare group. So in this language that I just established, what holds is that the translations are a unique subgroup of the Poincare group. So when I take a general transformation, a general Poincare transformation, I can tell you exactly if it is or if it is not a translation, because I only have one subgroup of translations. I don't have many copies of the group of translations. If you gave me the Poincare group not in this cute form with lambdas and a's, which is the way I wrote it, but instead you decided to use a very different notation, a very abstract notation, which would be, for example, let's see, you have here 10 parameters, you have 6 parameters in lambda and 4 parameters in a, and you just decided to give me this list of many parameters, which we're going to call, let's say, B, C, D, E, F, etc. And it just gave me all of these numbers and how they combine. So you would give me the group law, and you give me this list of numbers. In principle, I can look at it, and I will have no idea whether this element is a translation or if it is a Lorentz transformation, or if it is a combination of both. But if I know the algebraic structure, from the algebraic structure alone, from the product alone, I can figure out which of these elements are translations, because R4 is a normal subgroup of the Poincare group. So I do have this uniqueness property. And so the next natural question is then, does it hold that the Lorentz group is a normal subgroup of the Poincare group? And the answer is no. It is not a normal subgroup. To do this, we can simply do the same calculation as before. We take the inverse, we take here a general Lorentz transformation, and we take the original Poincare transformation. I should add lines somewhere here. What is the notation I use here? Okay. So I add a line here, now I add a line here. And this is going to be given then by lambda prime minus 1 minus lambda prime, messed up, minus 1 d times this composition here, which is going to be given by lambda prime, lambda b. Then you open this calculation, and what you're going to find is that you have this lambda prime minus 1, lambda B minus lambda prime minus 1 B. So this is the general transformation when you do a conjugation with a Lorentz transformation, and you see that this guy in general is not zero. So in general, when you conjugate a Lorentz transformation by elements of the Poincare group, what you get at the end is not a pure Lorentz transformation. If B is zero, then this guy is zero. And this, of course, makes sense because if B is zero, then what we get is a conjugation by Lorentz transformations, and the Lorentz group is a group. So this should indeed happen. But if B is not zero, if we have a translation, then what happens is that in general, we will not get a vanishing element in here. So we actually get something weirder. You get this combination, you conjugate a Lorentz transformation by Poincare transformations, and the result is not a Lorentz transformation. It is a more general Poincare transformation. So the Lorentz group is not a normal subgroup of the Poincare group. So while I can tell from the algebraic structure alone whether something is or is not a translation, I cannot do the same with Lorentz transformations. If I just pick the algebraic structure, if I just mess up my notation and get this lists of 10 points of 10 numbers, giving me each of the Poincare transformations, I will not be able to tell you which of them are Lorentz transformations because there is some ambiguity in this. So there are many different ways in which I could define this is a Lorentz transformation and this is not a pure Lorentz transformation. So there are many ways in which I could define this symbol here differently. So I could use many different ways, many different decompositions with this sort. The translations always agree, but the Lorentz transformations may not. So if in this notation I have that lambda 0 is a Lorentz transformation, I could just change notation somehow and get to some other notation in which this is actually lambda prime a, and this is now a Lorentz transformation. So you get this thing which is slightly more complicated. Yet if you grab 0a and you transform it, it is always going to be a 0a prime. So the a can change, the number can change, but the Lorentz factor doesn't change. So you have this curious structure when we're dealing with the Poincare group. And so actually write up both of them and to merge them together into the Poincare group, what we do now is the following. First, we notice that if we pick this subgroup as we wrote it before, so this is the subgroup of the form lambda 0, and we then take the intersection with the translations, we're going to find that the only Poincare transformation that is in this intersection is going to be the identity. Because since I am dealing with a translation, I can't have a Lorentz transformation. Since I'm dealing with a Lorentz transformation, I can have a translation. So the only way that can happen is if they both are the identities. So I get the identity. And furthermore, I want to point out that I can write lambda a in the form lambda 0 times 1 lambda minus 1 a. Or analogously, I can also write this in the form 1a times lambda 0. So an arbitrary Poincare transformation can be written as a translation and then a Lorentz transformation, or as a Lorentz transformation and then a translation. The reason we can do in both orders is precisely because the translations are a normal subgroup. So you see, when you have a normal subgroup, you have G minus 1 and G equals N. And if I just multiply by G on the left side, on both sides, we get, sorry, you don't have this -1. You get this thing here. So you can just change the order. It doesn't mean that the product is commutative. So you see that in here, when I change the order, I also change the elements. This guy is not this guy. But I can always find a way to express the product in the other order. And so since we have this property here, we can write the following. We can write this, the Poincaré group, as being the Lorentz group times the translations. What this means is that all Poincaré group elements are a translation followed by a Lorentz transformation. And now I should point out, recall this other property here. Why am I recalling this? Because this property and this property together define what we call a semi-direct product. So what is a semi-direct product? Let G be a group, E the identity, N a normal subgroup, H a subgroup. And now, if G equals H times N, which means that it is of the form Hn for H in H and N in N. Since N is normal, this is also equivalent to saying that G equals to N. H, the order doesn't really matter. And if the intersection of these two guys is the identity, then we say that G is the semi-direct product of H and N. We write it like this. So this is the symbol. This here is the symbol for the semi-direct product. So this is just a silly definition of what we call a semi-direct product. The reason this is important is because we can decompose this as products. So this is actually what I promised earlier. But also something else that you could do, I'm not going to cover this here, but something that is possible in group theory is for you to start with two arbitrary groups. You start with a group G1 and a group G2, and you can then define a larger group, G1 times G2, and it will hold that G2 is a normal subgroup of the full group. So you can build larger groups from starting groups and get a more complicated theory. And the reason I'm focusing on this here, the reason I'm discussing semi-direct products, it might be a little bit abstract at this point, but it's going to be important when we discuss DMS symmetries later, because the Poincaré group, as a spoiler, the Poincaré group is SO plus 3,1 product with R4. The BMS group is the product of the Lorentz transformations with the additive group Symmetry S2. This here are the smooth functions on the sphere S2. And what is important for you to notice here is, notice that the Lorentz transformations still look the same. So you still have the Lorentz transformations in exactly the same way, but the translations were generalized to this group, which is much larger. So when you're going to talk about a translation, you only need 4 numbers because these are the components of the vector in R4. Oops, let me just send here the form. Here's the form. So you only need 4 numbers for a translation in 4 dimensions, But now, when you go to the BMS group, you generalize the translations to this thing here, which is a whole function on the sphere. And since the sphere has infinitely many points, you're actually given infinitely many numbers, and thus this time what you get is an infinite dimensional group. A question: you always need a bigger group to generalize symmetries. I mean, if you're going to get more symmetries, you're going to need a bigger group. If you take a smaller group, then you're considering less symmetries. So, for example, if you consider only the translations, this is a smaller group than the Poincaré group, and now you have less symmetries because instead of having a 10-dimensional space of transformations, you now only have a 4-dimensional space. If you want a larger space, you need to add more dimensions. You need to make the group larger. Does that make sense? Okay, I'll let you think about it, and you tell me later. Feel free to ask again if it was not clear. All right, so this is what a semi-direct product is, and we will get back to this later. But for now, this concludes what I wanted to talk about within group theory, and we can get started with a bit more differential geometry and symmetries in curved spacetime. So this is going to be in curved spacetime. This is going to be a little bit technical at first, but we will soon get to more straightforward calculations. And those are going to be useful topics because when you're studying more advanced topics in general relativity, they become quite important. And you see, symmetries in curved spacetime end up being something very important because you want, for example, to impose. Here's a nice example. There is a problem in Wald's book. It's Wald. I think it's in chapter 6, which is on the Schwarzschild solution. And he wants you to find the most general electromagnetic field, which is both static and spherically symmetric. So what we want to discuss now is precisely how can I solve these sorts of problems. So I want to find the most general, it could be the most general metric, the most general tensor field of a certain rank with certain properties, the most general thing, so to speak, satisfying some symmetry considerations. And this is interesting because if you are assuming symmetry considerations in your problem, you can greatly simplify it. So for example, in here, if you are consider a spherically symmetric spacetime, it could be interesting for you to get the most general spherically symmetric metric, for example, because that allows you to discuss what is the most general spherically symmetric star, or the most general spherically symmetric black hole, or things like that. So it gives you, it restricts a lot the Einstein equations, and you get to much simpler equations. And in this way, you have a precise notion of knowing how much symmetry you are actually imposing, and what is the most general expression you can find within those constraints that you are imposing. And to discuss that, we are going to need a little bit more of differential geometry, mainly because we want to get to what we call Lie derivatives, which are the concept of derivatives that are really relevant for discussing symmetries in curved spacetime. And this must begin with a few silly discussions about maps between manifolds. So what we're going to consider here is we have two manifolds. One of them I'm going to call M, and the other one I'm going to call N. So we have these two manifolds. Let me give you a different drawing. So we have these two manifolds here. If you find the word manifold terrifying, you can just think of it as space-time, and that works just as fine. After all, that is indeed the main application we're interested in. So we have these two manifolds here. And I'm going to consider, for starters, that we have a map between them. So I have a function phi that eats points in M and splits points in N. So I'm going to have a function like this. I'm going to assume phi to be smooth. So every function we do in here is going to be smooth, unless it isn't. So I'm going to assume phi to be smooth. And later we will be interested in what we call a diffeomorphism. Diffeomorphism. Morphism in mathematics is a general term to mean a map that preserves the structure of the spaces you're considering. So here, diffeomorphism means morphism means that it preserves structure, and diffeo means that it preserves the differential structure. So the way in which you do calculus in both spaces is the same. And a diffeomorphism is a smooth function with smooth inverse. It is possible for a smooth function to not have a smooth inverse. So for example, just for a quick example, consider the function f from 0 infinity to on the semi-interval that goes into the real. No, I'm gonna take from to 0 infinity again. So I'm gonna consider this function here, and it takes x into x squared. Then the inverse is the square root, and the square root is not smooth at 0. So you have a few difficulties. This is the stereotypical example. I may be missing a few details here, and in the domain, maybe this domain needs to be open. I don't really recall all the details right now. But if you look up examples of smooth functions that don't have smooth inverses, you will find examples because these guys exist. So you actually need to impose that the inverse is smooth. This is different from the case of a homomorphism in groups, because the inverse of a homomorphism, when it exists, is always a homomorphism as well. So for now, we want phi to be smooth, and we have these two guys in here. So I'm gonna, instead of making those drawings, I usually prefer to draw diagrams, which are very common in math. So I'm gonna write it in this way here. This is very common in category theory, but I just find it a nice way to visualize how all the functions operate without getting crumbled up in a lot of drawings. So we have this function here, and I'm gonna assume I have another function, which is a scalar function on n. So I have these two functions here. I have the map between m and n, and I have the scalar function f. Now, one interesting construction that we can do in differential geometry is what we call a pullback. A pullback is pulling back this function here to become a function from m, from this guy, to r. What I'm going to do here is define this new function, which is going to be, I always get a little bit confused, f composed with phi. And this new function here is now a function from m to the real numbers. So I pulled back this function to this manifold. So I started with this, with a function in the range manifold, and I pulled it back to the domain manifold. When I talk about range and domain, I'm referring to this smooth map here. So I'm doing this pullback. And we have a special notation for this. When we want to discuss the pullback of f, we usually will denote phi star of f, and this is just f composed with phi. But the reason I'm introducing this notation is because when we get to tensor fields, it is going to be a little more complicated, and we would not have this notation here anymore. So this is the basic idea. This is how you pull back a scalar function. A comment about notation is important here. I like to write pullbacks with this notation. Mathematicians like to write pullbacks with this notation, with a star at the upper part, an up star instead of a lower star. This is just a notation convention. And if you're reading a book in differential geometry, you should look out for this, or you might get confused. The notation I'm using is the same one that Wald uses in his general relativity book. So I think that at least in general relativity, it makes more sense to follow this notation here. But if you're studying differential geometry, you may need to be careful about this. So this is the first structure. Now we can go a bit further. So consider again the manifold M, and consider a point P in M. In this point P, we can define what we call the tangent space to M at P. This is usually denoted TPM. And what is this? And this is the differential geometric notation. I really like it, so I'm going to stick to it. But this guy here, T stands for tangent, and this is the space of contravariant vectors at P. So this calls for drawing since we're doing geometry. So I'm going to have some point here. This is my manifold M. This here is the point P. And TPM is the vector space that is tangent to M at P. So in an extrinsic point of view, you can picture TPM as being the tangent plane to the manifold M at P. And this is going to be a vector space because it is a plane. And here live all the vectors, all the possible vectors at the particular point P. So this is TPM. And since we have the map phi, we can also consider here, using the map phi, we can go from this point M, P in M to the point phi of P in N. So we got this other point in M. And the question is, how do we relate the vectors at P in M to the vectors at phi of P in N? So how do we relate this to vector spaces, TPM and T phi of P N? How exactly do we do this transformation? And what we do now is not a pullback. What we can do now is a push forward. So instead of pulling back something, instead of pulling back a function, we can push forward a vector. What do I mean by that? What I mean is, suppose you have some vector V in the manifold M. It lives at the point P. So this is a vector specifically at the point P. What I can do is now define a vector that I call phi star V that lives in T phi P N. And now you see why I said that the position of the star is actually important, because the push forward has the star in one position and the pullback has the star in the other position. After you think about it for a while, you eventually get the hang of the notation you're using. But at first it can be a little bit confusing, so I'll be saying the names out loud. And we won't use this structure for much longer. We will only use it to get to Lie derivatives. So the push forward of the vector, it now lives on the range manifold, on the target manifold. And how do we define this guy? Well, we define this guy in the following way. Recall first that a vector in TPM means that V is a map from the smooth functions on P This means any function that is smooth at the point P, and it maps to a real number. So an example of a vector here would be the derivative along any coordinate. So the derivative along a particular coordinate, let's say the x coordinate. And what you do is you eat a function. So you're going to take the derivative of x, and then you evaluate it at P. So you need to evaluate it at P because we're considering a vector at P. If we do not evaluate at P, we do not have a vector, we have a vector field, which is a more complicated construction that I'm not considering right now, but we will consider it later. So a vector is something like this. A vector is something that eats a function and spits a number, and it does so in a way that resembles a derivative, because deep down it is a derivative. So the way I will define this guy here is going to be the following. If I have a function f from n to r, I'm going to define the action of this vector on that function by saying that you compute the action of the original vector in the pullback of that function. So how do I push forward a vector? What I do here is the following. This eventually starts getting a little more messy, so to speak. So we started with that diagram. We had m here, we had n here, and we had a function here. So we had this guys here, and then we had this pullback here. We pulled back the function. Now we can push forward the vector by considering the smooth functions at P, the smooth functions at phi of P. And what we do now is we have a pullback that pulls back the smooth functions in N to the smooth functions in M. And I have here a vector that eats a smooth function and spits a number. And what we can do now is we combine both these guys to get the push forward, which is going to do something like this. When you say a smooth function of P, do you mean a smooth function in the neighborhood of P? Yes, precisely. So this infinity P is a smooth function, is a function that is smooth in a neighborhood of P. So there is some neighborhood of P, there is some set, there is some open set surrounding P. So you have this P here, and you have this smaller set, this small set around P, and the function is smooth on this set. Different functions may have different neighborhoods, but this is the idea for infinity P. You do need a neighborhood. So that is the idea. You're welcome. So we get this. We can push forward a vector. And the reason here is this, that if we had a scalar function, we can pull it back. So it now becomes a function from the domain manifold into the real numbers. If we had a vector, we can push it forward to become a new vector from the target manifold to the real numbers. The next step we can do is a one form, which I like to call it one form, but some of you may know it as a covariant vector. And now what we have here, these guys, they do not live in TPM. They live actually in a new space that we call TPM star. The star here refers to the fact that this is the algebraic dual of the TPM. But that doesn't really matter right here. This is just the name of the space in which they live in. Oh, there's a question. How can we be sure that the push forward of V is on the tangent space of N? Yes, you can work out the details. The first thing we get here is this construction surely leads to a map that eats functions and spits numbers. So this is the first step that we need. Next, to ensure that it is indeed a vector and not only a function a map that eats functions and spits numbers, because we could have maps like that are not vectors, you have to verify a few other conditions. Namely, what really defines a vector is that it not only is a map like this, but it also is something that we call a derivation. A derivation is a function of this sort with the property that f of a product of functions equals to f of p vg plus g of p vf. This is, of course, just the Leibniz rule. So a vector, by definition, is a map that does this. It's a function and spits a number, and it satisfies this condition here. We call this a derivation. You find this definition in books in differential geometry, in Wald's book in general relativity. There are other equivalent definitions. So there is also another definition in which you consider curves. So a curve, recall, is a map from R into the manifold. So you can consider a curve, gamma, passing through P, and you can consider this its directional derivative. And this is going to give you another sense of vector. So have these two definitions of vector, and in usual differential geometry. So when you make the standard assumptions on what a manifold is, these two notions coincide. By standard assumptions, I'm going to make a comment here that uses a difficult word. If you never heard of topology before, you don't need to worry about this. But what you need is for manifold to be Hausdorff. If your manifold is Hausdorff, these two definitions coincide, but it is easier to work with derivations. So using this notion of a derivation, you can just pick this definition of push forward that I gave, which is this guy here. And notice that this here equals to V of F composed with phi. And you can now just consider different functions, and you will find that indeed this is a derivation. So you do need to fill in the details. I'm not giving all of the details right now, but you can show that this is indeed an element in the tangent space of N. But indeed, you do need to do a little bit more things than I actually did here. You need to carry out the proof that these guys are indeed derivations. You're welcome. Just as a curious remark here, I should mention that this push-forward map can also be understood as the derivative or the differential of the map between the manifolds. So if we have this map phi between M and N, phi star, which is going to be a map from TPM to T phi P, and can be understood as the derivative. And the reason is the notion of derivative in many dimensions. When you're considering, for example, calculus in many variables, what you have is going to be precisely something like this. So this would be the manifold analog of, for example, the Jacobian matrix. So the Jacobian matrix is the derivative of a map from say Rm to Rn, and here is it's the same idea but in manifold columns. So this is the idea of the differential, the derivative of this map phi between manifolds. Anyway, the next thing we get to do is to now discuss covectors. So covectors are covariant vectors. You can use whichever language you prefer. So here, covariant vector or covector or one form. I usually like one form. But what we have here now is that they live in TPM star or in T phi PM star. The star simply indicates that this is a covariant vector rather than a contravariant vector. And in algebra, this is called an algebraic dual. Dual is dual. So you have this construction now. And what happens now is that what is a covector? By definition, a covector omega is going to be something that it's a vector and spits a number, and it does so linearly. Oh yes, I think I forgot to mention this, but vectors also need to be linear. Linear in the functions, I mean. Linear? Yes, linear. So they do this linearly. So what I meant is that derivations are not enough. You actually need linearity too. So you get this definition here for one forms or covectors. And so the construction we're going to make now is the same thing. We write down the spaces we had before. I'm writing the spaces in the domain of the one forms. So these are the domains of the one forms. And what the one form does here, it eats a vector and spits a number. And what we have here is a map, which is the push forward between TPM and T5PN. So what we can do now is a pullback. So we have a form in the range, and we can pull it back to get a form in the domain. And the definition for this is going to be that the pullback of the form omega when acting on a certain vector v is going to be simply omega, the original omega, acting on the push forward of the vector v. And in this way, you just go doing this silly little play where you have the push forward, and then the function that eats that structure that has the push forward actually has a pullback, and the function that eats that structure that has a pullback then has a push forward, and just keep reversing them. However, you do end up at this point here, since if you go even further, if you now go to things that eat one forms, if you now go to a structure big V that eats a one form and spits a number, this is actually the same thing as a vector. And this is because in finite dimensions, it holds that the double dual or B dual is actually equal to the original space. This is a result from linear algebra. So you can't go any further. You end up at that point. But you can go to tensors now. So I can discuss if I have a 0L tensor, I can now discuss the pullback of this tensor field. This is a tensor field that eats many vectors. It's L vectors. And this is going to be given by T eating the push forwards of all of these vectors. So I can generalize this construction to tensors. And similarly, if I have now a K0 tensor, let's call it S just to make it different, what we can get now is a push forward of S. It eats a lot of one forms. I can discuss it as eating a lot of one forms precisely because of this equivalence here. So now I get this construction here. So a tensor is something that eats a lot of one forms. And this guy here is going to be given precisely by S feeding on the pullbacks of each of these one forms. So what if I have a more complicated tensor? If I have a mixed tensor? So now, for example, I have a 1-1 tensor. What can I do with that? A 1-1 tensor would be something that eats a vector, eats a one form, and eats a vector. So this is, for example, a matrix. In components, I would write this thing here in this way. So you see this guy here eats a one form, and it eats a vector. So it would have something like this. When you do this combination here, you get a real number. So the object is this guy here. It eats a one form and it eats a vector. And how do I do with this guy here? And the answer is you don't. If you have a general map between manifolds, you can't really do any neither pullbacks or push forwards. You can't do any of them. But you do have a better situation in the particular case in which your smooth map phi is a diffeomorphism. Is a diffeom. And the reason is because now you can define, say, the pullback of this tensor field, of this tensor that I'm considering. Since I'm doing a pullback, I'm considering that T is a tensor in the manifold N. And the pullback of T omega V is going to be given by T. I can't do a push forward in the one form, but I can consider a pullback with the inverse. And then I take the push forward of the vector. So this is the trick. This is how you deal with pullbacks and push forwards of more general fields, more general structures. What you actually do is you're going to need a diffeomorphism, which is more than a smooth function. It is a smooth function that has a smooth inverse. And then you can use the inverse to do these sorts of constructions. And the same thing goes to more general tensors. I used the example of a 1-1 tensor, but that is the very same idea for a more general construction. So why exactly do I care about this thing? And the reason is I want to discuss the derivatives and also the notion of a symmetry. Because you see, I have now these transformations. I have this map that goes from M to N. And in general, suppose now I pick not a map that goes from M to N, but suppose I get a map that goes to the same manifold. And I'm assuming, of course, that this guy is a diffeomorphism. So I'm sticking to the same space-time, but I'm doing this transformation that doesn't really, that shouldn't really change anything. And what happens to my tensor field? In particular, what happens to my metric? And I have two options. When I consider the transformation here, it could happen. The first case is that when I transform my metric, I actually get something that is not my original metric. And the second option is that I transform my metric and I get the very same thing. Now, this thing here is similar. It is actually the same thing, but from a different point of view, for me performing a coordinate transformation that changes the coordinate components of the metric. So diffeomorphisms are actually the same thing as coordinate transformations. So coordinate transformations are the basic example of diffeomorphisms, and they're just two different points of view of actually the same thing. And what this expression here means is that I changed coordinates to something in which the coordinate components of the metric are no longer the same. So, for example, if I change from Cartesian to spherical, this is going to change numerically the values of the metric. So in this sense, it does change the space-time. But of course, this is meaningless because I can use any coordinates I want to describe the physics. So this is something we call gauge invariance. So this is what we call a gauge symmetry because it isn't really changing anything physical about the space-time. It is actually just a redundancy in my description. So since I'm using differential geometry, I have this freedom in choosing coordinates, and that is a freedom I have in my theory that allows me to make choices that don't really impact the physics in any way. So I can use whichever coordinates I want, and that is not going to change the physical situation I'm dealing with. It is just going to stay pretty much the same thing. So I didn't really change anything. And we call this gauge invariance. So we say that general relativity, many people say actually, but there are some caveats to this. But it is common to say that general relativity is a gauge theory where the gauge group is the group of diffeomorphisms. This should be seen with some care because the ways in which you actually this is not actually meant in the same way as in other gauge theories. But I'm not going to focus on this right now. And the other case, which is the case I'm more interested in, is that we not only have this redundancy, but actually are going to have the same thing. So when we did this transformation, we didn't change anything. We didn't even change the coordinate components. And this is what we get when we actually have a physical symmetry. So this here is a physical symmetry. of the metric in this case. So this guy here is preserving everything I wish to preserve. So it doesn't change anything at all. It is the very same structure. So this guy here, it preserves the background spacetime, but it can change the tensor fields. And typically what this means is that, for example, if you had some tensor components, T, mu, rho, sigma, eta at some point, you will still have these components, but at someplace else. So things have changed in this sense. But now we're saying that your transformation not only preserves the differential structure, not only preserves the backward space-time, it also preserves the metric. This is what we call an isometry. And this is a physical symmetry of the metric. So this is what we mean when we say that the space-time is symmetric under some transformation. So in particular, you can now bring together all of the phi's that do this and make up a group with them, where the group product is going to be the composition. So you have some phi1 times phi2, and this is going to be the group product you have. And the group of all phi's with this product here is going to be a symmetry group for your space-time. And as an example, we say that a space-time M is spherically symmetric if the symmetry group has an SO3 subgroup. So this is how you implement symmetries in curved spacetime. This is how you discuss these things. But this is the most technical approach. So how do you actually get to do calculations? And the answer is with something we call Lie derivatives. So we now want to discuss this in a more local, a more infinitesimal way. So instead of assuming we only have one map, phi, let us suppose we have a collection of maps, phi t. So t here is a real number. To be completely rigorous, I should actually consider this as living in an interval inside the real line, but I will ignore these details, which you can find in any book in differential geometry that discusses, pretty much any book in differential geometry. And I'm going to consider this here. So this is a family of many different diffeomorphisms. And I'm going to assume that they form a one parameter group of diffeomorphisms. By this, I mean that they not only have this behavior, that there is a whole family of diffeomorphisms, but also I'm going to assume that phi t composed with phi s is always given by phi t plus s. So this gives what we call a one parameter group structure. So they have this special behavior. I can compose them in this very simple way. And what I'm interested in doing here with these guys is going to be the following. First, notice that if I pick point P, I can define a curve gamma P of T. This curve depends on P because it's the point where the curve starts. And this is going to be given by phi T of P. This condition in here implies that phi 0 is the identity. So at t equals 0, this curve starts at P. But then as t passes by, as I change the values of t, this will take me to other points. And I get a curve in the manifold. So I have this sort of structure. And what is interesting is that I can now consider many different values of P. I pick many different points in my manifold. And I'm going to have what we call a flow. I'm going to have all these guys here, which are giving me different trajectories depending on where I start. And I can then just consider the derivative of each of these curves at 0 And this is going to give me a bunch of vectors. So now I have a vector here, 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 and I have a vector at every point in the manifold. And what this means now is that I managed to construct a vector field from my family of, from my one parameter group of diffeomorphisms. So now I change the diffeomorphisms for a vector field. And similarly, using standard results from the theory of ordinary differential equations, you can start with a vector field like this one here, and you can integrate this vector field to get a one parameter group of diffeomorphisms. There may be some troubles with the domain of this family. So for example, it may happen that it is not defined for all values of t. But I'm not going to focus on those details here because they don't really matter for us. Okay, and what I want to do with this now is the following. I want to now consider this family of diffeomorphisms, and as I change this parameter, I would like to know how a given tensor field T changes. So I would like to compute this derivative here, this idea. So as I change the value of T, how exactly does my tensor field varies at the point P? And in silly symbols, so to speak, I would write this here as being something like a limit as T goes to 0 of the tensor at P plus T minus the tensor at P divided by T. Now, this here is meaningless because none of the symbols are really defined. So for example, P is a point in a manifold, then T is a real number. These guys don't even live in the same space. So this thing here is completely ill-defined. It doesn't make sense at all. But I want to get to something with this notion. And what we can do is use what we call a Lie derivative. So I'm going to do the following. Fix this one parameter group of diffeomorphisms. And this guy here gives you a vector field V. I'm gonna VA. So A is just the abstract index to recall us, to remind us that this guy here is a vector. What I will define as the Lie derivative along the direction of this vector field V. Remember that these guys here are in bijection. So if I have a vector field, I have a one parameter group of diffeomorphisms. If I have a one parameter group of diffeomorphisms, I have a vector field. The Lie derivative L, this is usually written with this pound sign or the Sterling pound sign of a given tensor, which is going to be A1, AK, B1, BL. I'm going to define this in terms of a push forward with minus T of the tensor minus the original tensor divided by T. And of course, I'm taking the limits as T gets small. This expression does make sense because this here is a tensor at P. And what exactly is this guy here? What this is telling me is you pick the tensor. So this guy here is a tensor at P plus T. And this push forward with minus T is pushing P plus T to P plus T minus T equals P. So what we are doing here is we pick the tensor a little bit further, then we are going to bring the tensor back to the point we're actually interested in. We subtract the original value of the tensor, divide by T, and this gives us our notion of derivative. So this is what we call a Lie derivative. This is completely different from what you would get if you were to compute something with the covariant derivative. Okay, so this is not the same thing. This is a completely different notion of derivative. And in particular, this notion here, the covariant derivative, requires a metric. So it requires a metric or a direct definition. So you can avoid using a metric if you define what you call nabla. But nabla is an extra structure on the manifold. The Lie derivative is available on all manifolds. You can always talk about the Lie derivative. It may not be convenient, and it does not represent the same thing as the covariant derivative, but it is always defined. So you can always talk about symmetries of a manifold. And what we have here now is this Lie derivative has a few good properties. I'm not going to prove them all just to save some time. But for example, it behaves nicely with tensor products. So if you have a tensor product here, this is going to be given just by the Leibniz rule plus VS tensor T. You get stuff like this. In the notes, you can find the properties of the Lie derivative for many different options of tensors. For example, if you have a function f, this is just given by the function evaluated at the vector. So recall that the vector is a derivative. So if you have a function, the Lie derivative just acts like the vector. Things get a bit more complicated when you start dealing with other tensors. So for example, the Lie derivative of a vector WA is actually given by what we call the commutator of V and W. This thing here can be written in terms of the covariant derivative. First, let me write this. This guy here is going to be a vector, elite function f. If you feed the function f to this guy, what you're going to get is this guy here, minus W V alpha. So it is a commutator in the sense it commutes the two vectors. And if you want to write this directly using, if you have a covariant derivative and you want to use the covariant derivative, this thing here is going to be given by this thing here. Okay. So this is the expression for the covariant derivative of a vector. You can keep playing with these guys here. You also have the expression for one form. You have the expressions for a very general tensor, and you just get expressions that are more and more complicated. And you can find them, for example, in Appendix C of Walt's book on relativity. So here, this is the expression for a one form. And it keeps going. You have there's lots and lots of expressions. Let me just see. Do I have? Okay, we still have 15 minutes. It's sufficient. And something that is particularly important for us, I should mention, you don't have to use the covariant derivative actually. I said covariant derivative, but actually that is too restrictive. You can use any derivative operator on your manifold. So this thing here, you don't have to have this condition. Is okay. So the derivative operator may not be compatible with the metric. You can use any derivative operator in here. In particular, you can use the standard derivative as long as you use it in every point, in every piece, in every term of the calculation. So you can use the standard derivative. You don't really need to use a covariant derivative. You can use whichever one you want. And this is useful because for some calculations that we're going to do, it will be useful to use some derivative operators that are not the covariant derivative. Okay. A particularly important case is when we consider that of a metric. And this is going to be given by this thing here. GAB. I can never remember what are the expressions for these things. Minus, no, plus. CB. nabla A BC plus G AC nabla B BC. Okay, this is the expression when you have a 0-2 tensor field. So this can be rewritten in this way here. If the metric and the derivative operator are compatible, so now if it holds that they are compatible, then this first guy vanishes, and the second guy becomes just this thing here. So we got this expression. Why exactly do we care about this? Because now we can get to the notion of a conformal Killing field and more general Killing fields. What happens here now is the following. Suppose that you have a family of symmetries. So you have something here that behaves. Oh, sorry, it's a 0. No, it's a G. It's a G. So you have something that behaves like this for every value of t. So you have this thing here for all t. Then what exactly does this thing means? It means that you have a family of symmetries. And the idea here could be, for example, that these guys are rotations. So maybe for each value of t, you have a different rotation angle. So you can rotate it very slightly. So it could be very small here, infinitesimal even, or it could be very large. And you can just go changing these values of t. So if you have this for many values of t, you actually get a group, a Lie group, which is the one parameter group of diffeomorphisms. And if you have even more than one parameter group, you get larger groups. So this here is the fundamental definition for a continuous symmetry in your space-time. And here, if we want now, we can just reverse the sign of t. We can just grab it like this here, and we're gonna have that this holds if we have discontinuous symmetries. We can now just take this to the Lie derivative, and we're gonna find this result here. So this is the defining equation for a vector field V, which is called a killing vector field. Recall, as I said earlier, killing is a name, has nothing to do with killing anything. So this is what we call a killing vector field. It needs to be complete, so it needs to be we need to be able to fully integrate it to get all values of t to actually call it a killing vector field. So to actually call it a symmetry generator. So we have this thing here. We can also have something a bit more general, which would be in the case that we have phi star g equals a function omega square g. This here means that when you apply the transformation, you're actually changing the metric by a constant factor. By a multiplicative factor. This omega here is a function on the manifold, and you can then change the metric in this way. This thing here is what we call now a conformal isometry. It is conformal because this sort of transformation here is what we call a conformal transformation. This inflating the metric. And isometry refers to the fact that it is a diffeomorphism. So ironically, a conformal isometry is not an isometry, but it is conformal. And a conformal isometry is a diffeomorphism, which is also a conformal transformation. So it's something more general than an isometry. And if we now get this to the Lie derivative level, what we're going to have is what we call a conformal killing field, which is going to be something of this sort here, where lambda is the function. Okay, and this here is what we call a CKD, or conformal killing vector field. And you see, if we use the expressions for the Lie derivative that I wrote a little bit earlier, we use these expressions here. What we are going to find is that Killing fields are such that nabla VB plus nabla VA equals 0. And conformal Killing fields are a bit more general. They will have this appearance here. You have these two notions. So solving the Killing equation, if the vector field is complete, this here gives you the symmetries of your spacetime, and this here gives you something a bit more general. These are not the isometries; these are the conformal isometries. So you can also think of them as symmetries, but they are symmetries in a slightly different way. And to give an example of how we can use the Lie derivatives in that exercise for modes that I mentioned earlier, so the most general spherically metric ENM field, what you're going to do here is you're going to pick the Killing fields that generate a spherical symmetry. So I'm going to have to pick 3 fields here. These are the rotations. So for example, one of them would be the field given by this thing here. So this is one of the fields. The other ones are a little bit more complicated when you're using spherical coordinates, but they usually have an appearance similar to this one. And then what you're going to do is you're going to pick the 3 fields. So this guy here, let's say psi and zeta, and you're going to impose the conditions that L psi on the Faraday tensor must be 0. So this here forces one symmetry. And this is going to give you a few differential equations that you must solve for the components of FAB. Then you do the same thing for the other fields, and you can find the differential equations that need to be solved to enforce symmetry. These equations are typically kind of easy to compute and impose some restrictions on the components of your vector field. And this is why you can compute, for example, what is the most general spherically symmetric electromagnetic field, or the most general spherically symmetric metric, and stuff like that. In some situations, there is a straightforward argument to get on these things. So sometimes you can find a quicker way of arguing these things. But the most general approach that I know of, at least, is using Lie derivatives. Although it can be a little bit cumbersome, it may be a little bit of algebraic work. So we have these definitions. The final comments. Let me just go back to the conformal Killing vector equation. I think since we have not much time, this may be the best use of our time. We have this expression here. So this is the CKV equation. And it turns out that this lambda is not arbitrary. You see, we can just contract this expression here with the metric. And we're going to have here that this side is going to be 2 nabla A VA. And this other side here is going to be lambda times n, where this here is the dimension of spacetime. Or of the manifold you're considering. We will also consider spaces that are not spacetimes. So by solving this here, you find that the CKV equation is actually given by this thing. The lambda is given by this thing here. So the CKV equation turns out to be simply this guy here, which is a bit more objective than the version of lambda. Yes. So there's still things that I wanted to say, but it surely would take a little bit of time. So I think I'll need to leave it for tomorrow, and hope that we eventually catch up to the schedule. But something that eventually will work out. I think, yeah, in the future lectures there are lots of drawings, so we probably will manage to do this just fine. All right. Are there any questions at the moment? Okay. There doesn't seem to be any, so I'll stop recording and then ask it. Oh, yeah, there is a question. Did you write a minus t in the lower index of phi? Yeah, I believe you're referring to the definition of the Lie derivative. And yes, I did write a minus t. It's here. And the reason is because you're taking a tensor that is defined at p plus t, and you need to push forward to minus t. So it is a little bit confusing. But what you have here is you have your tensor living happily in p plus t, and you're gonna push it forward to p plus t minus t, which is equal to p. So your push forward is a push forward with minus t and t. I always found the definition of Lie derivative, which is the only one that I know. Yeah, you actually have a definition in terms of coordinates, but I don't really like using definitions in terms of coordinates. But I always found this construction a little bit complicated to understand, but with practice you get the hang of it. In the conformal killing fields, yes, in here I did do that. The reason is, if this holds for every t, this implies that this holds for every t. So I did this trick just so I could manipulate this expression into becoming this expression. So I did change t to minus t from here to here. But these two equations in here are actually equivalent. So I could have started with either one of them. I just did this change in, I just started writing it this way because I found it a little bit clearer. But then I wanted to change the notation to get to the expression of the Lie derivative. So, sorry for that, but yes, you can use a minus t here. Any other questions? So yes, the minus t over there is precisely to get the definition of the Lie derivative. The only reason I use the minus t is because I defined the Lie derivative with the minus t, so I wanted to do this. You're welcome. Any other questions? Okay, it doesn't seem so I'll stop recording. Find it here.